Hi, I'm Gary Stafford, a Principal Solutions Architect at Amazon Web Services. About a month ago, I published a technical article and produced an accompanying video entitled Multi-Vector Semantic Search, Advanced Vector Search with TwelveLabs and Amazon OpenSearch. At that time, TwelveLabs was not on Amazon Bedrock. In the article and the accompanying video, I demonstrated how to access the Marengo and Pegasus models on TwelveLabs' SaaS platform. Well, a lot has changed since then. Last Wednesday at AWS's New York Summit, TwelveLabs went live on Amazon Bedrock. Both the Marengo and Pegasus models are now available on AWS through the Amazon Bedrock platform. In this new video, we'll learn how to use TwelveLabs, Marengo, and Pegasus models on Amazon Bedrock to build a semantic search solution on OpenSearch for advertising, specifically television commercials. We'll step through all of the code necessary to build the solution end-to-end. First, using Marengo on Amazon Bedrock, we'll generate 3 types of vector embeddings from a series of television commercials. We'll also generate a title, detailed summary, and a list of keywords for each commercial using Pegasus on Amazon Bedrock. Then, we'll combine the embeddings with the title, summary, and keywords into a single OpenSearch document and index those documents into an OpenSearch vector index. Lastly, we'll learn how to perform semantic search across the index of commercials and how to visualize those search results. In order to follow along with the demonstration, you'll need to set up a local development environment with the necessary Python packages. You'll also need an AWS account with your AWS credentials and optionally Docker. As in the last video, we'll be using Docker locally as a substitute for Amazon OpenSearch serverless. But in this particular instance, there will be a fee for calling Amazon Bedrock for the embeddings and the analysis for the summary, title, and keywords. Let me start by stepping through the GitHub repository, which contains all of the code for this demonstration. This is the repository. The first couple directories are where we're going to store our assets. So we have one for videos. We also have one for keyframes, and I'll talk about that in a moment. We're going to generate some keyframes for these videos so we can visualize them. We have our OpenSearch documents in the document directory. And then we have 2 directories, one for the Marengo embeddings and one for the Pegasus analysis. So similar to the last video, if you watched the last video, we're going to be generating the Marengo embeddings as JSON files. We're then going to be generating the analysis, the title, keywords, and summary of each commercial, and placing those in this directory as JSON files. We'll then combine the 2 JSON files, which represent the video, the embeddings, and the analysis, into a single OpenSearch document. Again, we have the keyframes and we have our videos. Now, the videos and the keyframes we're going to be uploading to Amazon S3, and we'll be able to access the videos when we make our calls to Pegasus and Marengo on Amazon Bedrock. And we'll also be calling the keyframes later through a CloudFront distribution. There's also a Docker Compose file. So again, today I'm going to be using Docker instead of Amazon OpenSearch serverless, which is fine for demonstration purposes and for development and testing. We have our environments file. I'll explain what that is in a minute, but that's going to contain our sensitive environment variables. We're going to be renaming that as part of getting started process, just like we did in the last video. Next, we have a couple different Python files. I'll be explaining each one of these as we go through. We start off by performing or generating our embeddings using Marengo. So we have a separate script that'll do that. We also have a separate script that will generate our analysis. Again, we're going to be doing a title, a summary, and some keywords with the Pegasus model. So we have a separate script that'll do that for all of our videos. We also have a third Python file, which is going to prepare our OpenSearch documents, going to combine those analysis with those embeddings into OpenSearch documents that we can then push into our OpenSearch index. If you're interested in previewing your videos as part of the search, we're going to be generating keyframes using FFmpeg, and you'll need FFmpeg installed. We'll go through that in a minute. So there's a script to do that. And then we have our main notebook. Now, in the last video, all of this was combined to the notebook. It was a little bit overwhelming, so I've broken all that out separate. So we're going to be generating our embeddings, generating our analysis, generating our OpenSearch documents. And then when we have all of that done, we're going to go into our notebook. We're going to create our index. We're going to index those documents, and then we're going to perform our search. So the notebook this time is really focused on OpenSearch. And then there's also some helper files, and I'll talk about those in a minute, the data py file and the utilities py or Python file. Those are helper methods that we're going to be using throughout this in the notebook and in the separate Python files. So the README file, new diagram, and let me open that diagram just to walk through what the process is going to look like. So this is our diagram, a little bit changed from the last video and blog post that I wrote. Starting on the left-hand side, you can see we have our videos and our video keyframes. We're going to be uploading those into an Amazon S3 bucket, so you'll need an Amazon S3 bucket to get started. And then instead of using the TwelveLabs SaaS platform to create our embeddings and our summaries, in this case, title summaries and keywords, we're going to be using Amazon Bedrock. Now, I haven't showed all the individual Python files, but obviously those calls to Bedrock are done through the Python files. Bedrock will then access the videos that are in S3. It will perform an analysis, create the title, summary, and keywords. The Marengo model will also access those videos in S3, and it will break those videos down like we talked about last time into individual clips from 2 to 10 seconds. And then they will create 3 different types of embedding. So we're going to create a visual embedding, a visual text embedding, and an audio embedding. The difference between all of those is in the AWS as well as the TwelveLabs documentation. We're going to be taking those embeddings from each one of those video clips, so all those embeddings, along with the title, summary, and keywords that we generated for each video, we're going to be combining those into what's called a multi-vector nested OpenSearch document. So it's an OpenSearch document that contains multiple nested embeddings or vector embeddings. And then we're going to be indexing those into an OpenSearch vector index. And then once we're all done with that, we can start performing our semantic search. So that's the workflow that we're going to be going through today. Next, let me go through the README file and just tell you what you'll need to prepare in order to go through this demonstration with me. So you'll obviously need a current version of Python. You'll need AWS credentials. Even if you're using OpenSearch through Docker, we are going to be accessing the Marengo and Pegasus models on Amazon Bedrock. So you'll need your AWS credentials for the command line. You will need an Amazon S3 bucket. Actually, right now, you're going to need 2 buckets. I'll explain that in a moment. But we will need 2 buckets, one in 2 different AWS regions because of the way the models were deployed to Amazon Bedrock for the launch. Next, you'll need an Amazon OpenSearch serverless collection, and now that's optional. We're going to be using Docker, so for this demonstration, I won't be using Amazon OpenSearch serverless. And then if you do want to generate keyframes, and there's a lot of ways to generate keyframes, I suggest using FFmpeg. There is a Python package we'll be using, but in order to use that Python package, you'll need FFmpeg installed locally on your computer. Today, I'm on a Windows 11 machine, so I have FFmpeg installed on my Windows machine, and I have Python installed, so I'm ready to go. Next, for installation, the first thing you want to do is clone this repository. So we've cloned this GitHub repository to your local environment. Then we're going to rename the python.env file. So if you remember in our last video, if you watched the last video, I'm using the .env package, the python.env package, and that gives us the ability to store our sensitive variables outside of our main code. There is a env.txt file. You want to rename that to .env, as you can see here in the instructions, and there's instructions for Mac and Windows. And then within that file, you're going to want to add some environment variables. I'm putting my AWS credentials directly into that file. There's other ways to access AWS. There's other ways to access your credentials. For this demonstration, I'm going to be putting those into the env file and then loading those into the notebook specifically. I'm also going to be using those on the command line for the Python script. That's up to you how you access the region access key, secret access key, and session tokens. You can put those in the env file. Next, I mentioned the 2 buckets. Unfortunately for the launch, the Marengo and the Pegasus models are in 2 different regions. Marengo is in US East 1 and Pegasus is in US West 2. Now, we can use what's referred to as cross-region inference to access the Pegasus model, but as of today, my understanding is in order for the model to call a video asset, in order to perform that analysis or to create those embeddings, the S3 bucket needs to be in the same region as the model is being called. So again, my understanding, I need to put a bucket, one for Marengo in US East 1, and a copy of that bucket, and a copy of those videos today in US West 2 for Pegasus. And again, if I'm wrong, please feel free to correct me in the comments for this video. And I would expect that at some point, hopefully those models will be in the same region. The last thing we need is our OpenSearch endpoint. Again, if you're using Amazon OpenSearch serverless, you'll have an endpoint. If you're doing this locally with Docker, that OpenSearch endpoint is just going to be the word localhost. No HTTP or HTTPS, just localhost. The next thing you want to do is create a Python virtual environment. This is for both your Jupyter Notebook and for the Python files. I have directions for both Mac and Windows, although this isn't absolutely necessary. I highly recommend it. We're going to be installing a number of packages, and this gives you the ability to clean up your environment when you're done and delete that environment and not affect your local development environment in any way. The last thing I would suggest before we get going here is to make sure that you do validate that you have FFmpeg. You will need FFmpeg installed locally. A few instructions here. You will want to generate your embeddings using the Marengo model. We'll run that script. Then we'll generate our analysis, our summary, title, and keywords using Pegasus. Lastly, we'll prepare OpenSearch documents. We'll combine the embeddings with the analysis, and then we're going to be pushing those into OpenSearch and creating our OpenSearch index using the attached notebooks. There's also instructions here for running Amazon OpenSearch in Docker. So again, if you want to use Docker locally, that will reduce your cost. Again, this video is not going to be totally free, but if you want to save the cost of using Amazon OpenSearch serverless just for this demonstration, you can use Docker. You can see here that I have Docker Desktop installed. Again, I'm on Windows 11. I've also tested all of this on Mac, so it works just fine. And I've downloaded the OpenSearch projects, OpenSearch dashboards. We're not going to be showing that today. We're not going to be using the dashboards, although those are helpful for troubleshooting. And then obviously we have the OpenSearch image. So 2 images, those are the 2 images that we're going to be using. And then you can see here that I already have 2 containers already created, and we'll talk about that in a minute. So Docker Desktop installed and ready to go. If you are going to use Docker locally, we're going to create a Docker swarm. So we have the commands here for Mac and Windows. And then when you're all done, you can run this Docker service ls and wait for both of those images to download if it's the first time you're downloading the images, and then to instantiate the 2 containers and get that swarm running with the 2 containers that we're going to need. Also, some basic commands here. Again, if you use the OpenSearch dashboards, there is a Dev Tools tab, and then within the Dev Tools tab, I have some basic commands here. So once we get our index created, we can go in there and take a look at it. And the Dev Tools is good if you're generating new queries and want to design queries, sometimes a little quicker in there to iterate, and then you can copy those queries and put them directly into your Python code. So that's what you'll need to get set up and running. I'm going to switch over now to VS Code. Again, I'm on Windows 11. I'm running the latest version of VS Code. I've already cloned the GitHub repository, so I have that downloaded and ready to go. You can see all the same files here. For the sake of time, I've already run a number of these scripts. So we'll start with the embeddings script. And this looks at a particular bucket, assuming that we've uploaded all the videos into our S3 bucket along with the keyframes. So the keyframes and the videos are in our S3 bucket. The script will get a list of names of all the objects or all the videos that are in the S3 bucket. It will iterate through those. It will call Amazon Bedrock. It will call the Marengo model through Amazon Bedrock, and it will generate those 3 types of embeddings. So it will divide the video up into segments, and then for each segment, we'll get a visual image, a visual text, and an audio embedding. And then it will write that locally. So if we look in our Marengo's embedding, I've already done that. I have about 41 advertisements. You can see the names here and the name of the video and the name of the embeddings and also the analysis. I'm just using the same name for consistency. It's easier to find those and combine those later. I have the video name, the S3 URI, so where that video came from. I also have the keyframe. Now I've created a CloudFront distribution and I have all those keyframes available so I can preview those. I'll show you how that works a little later. I have the date it was created. I also have the size and bytes of the video, the duration, the content type. Again, these are all MP4 files. And then we have our embeddings, and we'll take a look at those in a little while. But we have multiple embeddings, obviously 3 different types of embeddings. This is a 60-second duration commercial that's been divided up into segments anywhere from 2 to 10 seconds. And then each one of those gets 3 embeddings. So we have a number of embeddings. We'll take a look at those in a minute. So this is what we're creating with the first Python script, which is the generate embeddings with Marengo. So using this Python script, I've already run this. You can run this. And as long as you have your videos in the correct place in S3 and you've filled out the environments file, I'll show you that in a minute. We'll run this and we'll generate all of our embeddings. The next step is to generate our analysis. So again, very similar. The only difference here is the region is going to be different. So I mentioned that US West 2 is where the Pegasus model is, not US East 1. We are going to be calling that using cross-region inference, generating 3 types of analysis. We're generating the title, the summary, and the keywords, and I have prompts for each one of those. There is also a way to use structured output, and that is documented in the documentation, and potentially get all of these back at once. I could not get that working. That might just be me. I could not get the code samples working properly. This worked just as good, so I made for each video 3 calls. I was able to construct prompt, which allowed me to generate a summary the way I wanted, a title, and the keywords the way I wanted. This generates those, and again, those will end up here in the analysis folder. We can take a look at one of these. We see the same thing as in the embeddings. I have the video name, the S3 URI, where it found that video that it processed, the title. We generated a title using Pegasus. We generated a lengthy summary. Let me wrap this. So you can see here, fairly lengthy in terms of a detailed summary. And then we have keywords. So we've used Pegasus analyzed a video, and we pulled out a set of keywords. And we can also perform hybrid search. So in addition to doing semantic search using the vector embeddings that we've created, we can also do keyword searches. We can do searches based on the summary or the title, or we can combine those and do hybrid searches. And we'll have some examples of that a little later on. Lastly, we have the prepare OpenSearch document. So this is our third script. This loops through the 2 directories, the Marengo embeddings and the Pegasus analysis. It combines those together into a single OpenSearch document, which we'll be able to directly index into our OpenSearch index. Now, you see there's reference here to OpenSearch document. There's also a video analysis and a video embeddings class. These classes exist in the data.py file, and I'm using Pydantic. So I've imported the base model, and I've created a few custom classes or data objects, and that makes it a lot easier so I can kind of customize how I want my documents to look. What else do I want to include? So let's take a look at the video embeddings. In addition to this video embedding segment is kind of the standard structure that you get back when you call the Marengo model through Bedrock, but I've added some additional fields. So I'm going to be generating the video name. I'm going to be extracting that from the list of videos. I'm going to have the S3 URI, so I want to know where that video came from. Again, I have a CloudFront distribution for the keyframe, so I have that included. I also have the date created, the size in bytes, the duration, the content type, and then I have my embeddings that I got back through my call to Amazon Bedrock. So this is that video embeddings object. That's when I call Marengo. This is what I'm creating. This is what that JSON file structure looks like. I've done the same for the Pegasus model. I've created a summary. I have the summary. I have a list of keywords, and I have the title. In addition, I have the video name. So I want to know the name of the video, and I want to know where that video that I analyzed was located. And again, I want to know when it's created in case I want to do it again or maybe backfill my index. Lastly, I have my OpenSearch document. So this is the structure of my OpenSearch document. This is the JSON structure for each one of the documents. The documents are in JSON. Have my video name. So I'm pulling all these fields that I've already extracted or created. I'm pulling all that together into a single OpenSearch document. And these are all the fields that are going to be available to search on in OpenSearch. So the video name, the S3 URI where that video was created. Again, a keyframe. This is an HTTPS endpoint that I can call and actually visualize that keyframe or see that keyframe. I have the title, the summary, and the keywords, which I generated with Pegasus, the date created for this document, again, in case I want to recreate it or do a backfill. I have the content type and the bit size. Now, those I pulled from the S3 object. I'll show you how I got those in a moment. Those were done by actually reading the S3 object, the video in S3, and I'm able to get the content type and size in bytes of the video. So those are also included. I also have the duration. So how long is the video? Oftentimes you may want to filter and say, give me all the commercials over 30 seconds or under 2 minutes. And then I obviously have my embedding. So this is what our OpenSearch document is going to look like. The only other file in here I didn't touch upon was utilities. And this is just a utilities class. So we have get list of video names. So for both Pegasus and Marengo, we want to get a list of video names or object names back. And we're going to iterate through all of those videos, create our embeddings, create our descriptions. Also want to get S3 object metadata. So I mentioned I'm getting the file size of the video, and I'm also getting the type. Now, obviously, these are all MP4s, but they may not always be MP4s. There's a number of ways you could use, since we're using FFmpeg, we could use FFprobe, but that would mean we would need the videos locally. If you don't have the videos locally, one way you can get at least those two fields is using the metadata that's included with each object. So we're doing a head object with the Bodo 3 S3 client, and we're getting that information back. The last thing is the polling job status. Now, we are doing asynchronous call with Amazon Bedrock, specifically for Marengo, uses the async method, which means we make a call, the embeddings are created, and the embeddings end up back in S3. So in addition to our videos and our keyframes, when we create our embeddings, at least for today, that's an asynchronous operation, which means we're going to make a call. That call goes off into a queue. We can keep polling till we find out that that's done. Once it's done, we can then pull those embeddings back from S3, put those into the right format, and eventually put those into OpenSearch. These methods are helpful. They're used by multiple scripts, so those are in the utilities py file. So those are all of our files that we have. I went through the directories before, the embeddings, the analysis, the documents, the keyframes, and the videos, and then I went through all of the files in here. Once we've done that, so we're going to end up with documents. We have our embeddings, our analysis. We've put our videos into S3. We've generated the embeddings analysis. We've combined those into documents. Make this demonstration short today, I've gone ahead and I've created all these ahead of time. We're going to get started with the notebook, and we're going to run through all the cells in the notebook. So the notebook's going to allow us to combine the video title, summary, and keywords, and all the embeddings which we've placed in this document. The notebook's going to allow us to index all these documents. We're going to create our index. We're going to index the documents, and then we're going to be able to perform several types of searches, including being able to visualize the commercials. The first thing you're going to want to do is install the required Python packages. So we'll update pip, and then we have all of our requirements in a separate requirements.txt file. We can take a look at that. Here's that file, so Bodo 3. We have a few plotting libraries for both visualizing and plotting some of the results. We have Pandantic that I talked about for those custom objects that we've created to hold our data. We talked a little bit about python.env, that's using the .env file to store our sensitive variables. FFmpeg, Python FFmpeg, if you're going to create keyframes, I'm using FFmpeg. And then the OpenSearch PY. So whether you're using Amazon OpenSearch serverless or you're using Docker locally and running OpenSearch in Docker, this is the library we're going to be using. So that's the other library that we're loading in here. So those are all the packages. You can see here that they're all installed. Now, if this is your first time installing those packages, you're going to want to restart your environment. So I'll restart my environment even though I had those loaded just in case there was an update. And then we'll continue on. We're going to load our environment variables using the load env class from the .env package or library. So we run a load.env command. This file is included in the GitHub directory. You'll rename this to .env. I won't open that since all my sensitive variables are in there. But what I did is I renamed this to .env and then I populated this. So my region, my access keys, my tokens, and then also my S3 bucket names. And again, I have two S3 buckets because again, today Marengo and Pegasus are in two different regions. And then I have my OpenSearch endpoint, which in this case is just going to be a local host for running in Docker. So I've installed all those. Those are all ready to go. Have some constants here. So the name of our index, OpenSearch index, is going to be TV commercials index. Where are our documents? So I'm just going to tell it where our documents are because I'm going to want to index all those. In order to do a search, so let's say we have a text search. I'm searching for all of the scenes where there's a car driving in the city, and we'll go through that example. In order to perform that semantic search, I need to convert that text string, that text query, into an embedding. So I need to know what model to use, and I need to know where to retrieve that embedding in S3 because, again, it's an asynchronous call, which means I can pass it a text string. It will create an embedding, but that embedding is going to end up in S3. I need to pull it back down to use that in my search. So that's why we have these fields here. The next thing we're going to want to do, now I have both clients in here. Option 1 is Amazon OpenSearch client. We're using Docker. You can run this. It's not going to break anything, and it's actually not going to break because we're not actually calling it. What I'm going to be specifically using instead of option 1, I'm going to be using option 2, which is OpenSearch client, again, running in Docker. In Docker, we have both of the containers running, so we have our swarm running. If you want to just double check that your swarm is ready, let me just jump back to the README for a minute and scroll down. There is a Docker service ls command, same as Windows and Mac. You can go ahead and run that on your command line. You can see here that I have OpenSearch and OpenSearch dashboards running, one replica of each. My Docker Swarm is running, those two containers are running. So when I'm ready to start using OpenSearch, you'll want to make sure that just everything is up and running. That's a good command to use. You can also see the ports 9200 is what we're going to be using to index our documents into OpenSearch. And then if you want to use a dashboard, again, both of these are on localhost. 5601 is the port that the dashboards are running on. When you first log into OpenSearch, it's going to ask you for a username and password specifically in the dashboard, and those are in the Docker Compose file. So if you go into Docker Compose, you can see here that we have the OpenSearch initial admin password is OpenSearch123, and then for dashboards, the username is admin. So admin and OpenSearch123, if you're wondering what those are. We can go ahead and run that. That's going to, option number 2 is the one that I'm going to be using. You can use either one depending on where you're going to be running it. The next thing you're going to want to do is create a new vector index, so an OpenSearch vector index or vector search. Now, a couple things, if you watch my first video, just want to call out at least 2 or 3 key things here. What makes this a vector index? First, we have KNN or K nearest neighbor to true. So that means this is going to be a vector index. The other key thing to keep in mind with TwelveLabs, the Marengo model, number of dimensions, 1024. So if you've created embeddings before, if you're using embedding models, those embeddings, the number of dimensions will vary. In this case, for Marengo, whether you're using the TwelveLabs SaaS platform or using that locally through Amazon Bedrock, 1024. So that's really key. You can take a look at some of these other settings, go through the OpenSearch documentation if you want to figure out what all these mean. The last thing I'll just show you here, which is key, is, and I mentioned these are multiple vectors, so each document contains multiple vectors. What makes them nested is right here. So if we take a look at the document structure, let me open a document. You can see here this document has a structure, and right here we have embeddings. So we have a list of embeddings, and within here we have multiple embedding objects. So we have an embedding object, it has an embedding, it has a few other key fields. Scroll down a little bit, the vectors are large. Here we also have the embedding options, so the type of embedding, visual text, visual image or audio, when it started and when it ended. So this is the length of the duration. So this one is slightly under 7 seconds. So that's our structure. Now how does that relate back to here? If you notice here we have embeddings, and then we have embedding. So this actually represents the physical structure of our document. It's nested, there are embedding objects, and then within there is an embedding of 1024 dimensions. So that's critical that we set our index up that way. So you can see here I've successfully created that index. Now I just ran that twice. Let me just delete that again. And we'll run that again. And there we go. So we just created that. If we want to retrieve information about it, and this is good just to make sure it was created successfully and to make sure that all of our configuration was right, we can run the indices get command and we'll see that we get the information back. So we have embeddings. Within embeddings, we have an embedding object, multiple embedding objects, 1024 dimensions, and KNN is set to true. So that looks good. So we're ready to go. Next thing I want to do is bulk index all of our OpenSearch documents. So again, I have 41 documents, which represent 41 videos. It's a combination of the embeddings plus all the summaries. We want to bulk index those documents into our index so we can run the next cell. And then if we want to quickly kind of run the next cell here, it indexes complete. By the time I ran this, it indexed those pretty quickly. I'm in a pretty fast machine. If your machine's a little slower, this will poll the index. And if you have a bulk, in this case, we bulk index 41 documents, this will check until the count in the index equals this count. And if not, it'll keep polling. It'll just let you know that it's working. It'll give you an update. For Amazon OpenSearch serverless, there's a minimum of 60 seconds. And this is where you're going to want to use this. There is a bit of a delay. So if you run this, just make sure that this runs to completion. And when it's completed, it'll tell you you have 41 documents, which matches the total number of documents which I index using the bulk index. So we're ready to go. I deleted my old index. I created a fresh new index. I bulk indexed the 41 OpenSearch documents, which represent our 41 television commercials. Pull to make sure everything is in there. So we have a new index, 41 documents ready to go. So what do we want to search for? We can see that I have a text search, which is right here, and it's cars driving in the city. Now I have another one here if you want to try it out. This is more of an audio one for a Pepsi commercial, boom, boom, boom to the baseline. This search though, there are several videos that have cars in a city. So they're city scenes with cars. So I know this search is good. It'll return some results. This one is also though useful again if you want to try audio later on. We'll be using both of these. What happens is this search is passed into the generate search embedding. And again, because we want to be able to do a semantic search, so we want to use an embedding to find the nearest neighbors or the approximate nearest neighbors, KNN or ANN. We want to generate a embedding from our text, and then we're going to do a semantic search and find the nearest neighbors using the vectors that we have in our index, and those will return those search results with a score. The key here is if you want to do a search, if you're a user and you're doing a semantic search, you need to convert your text-based search into an embedding using the exact same model, the exact same embedding space as the index was created in. So that's what we're doing here. And we can see that's running. Okay, and we can see that finished in about 31.5 seconds. Now, if you've used a TwelveLabs platform or saw my last video, you might be thinking, wow, that's a long time. Testing on the TwelveLabs platform to create the same embedding takes a fraction of a second. I'm not sure if it's my particular AWS account that I'm using to access the model. I would expect that to be much faster. So what happens is we generate our embedding, polls every 10 seconds, and it checks that this invocation is done. So the invocation ARN, we have an invocation ARN here for our asynchronous call. So we're using an asynchronous call, which is right here. So start async invoke with our Bedrock client. We're calling the Marengo model. We're passing in text input. We're passing in that search query string, cars driving in the city. That's going to get processed. An embedding is going to be created and it's going to get dumped out because it's asynchronous into S3 and we have that path right here. Now this did run successfully. Then we're going to download that embedding from S3. So we're going to, using that location, we know where the location is. We'll then call download search embedding and I'll extract that embedding. And then we'll use that embedding to do our semantic search. So we're ready to go. We can start doing our searches. The first search we're going to do is really the most basic search. So we're going to do a nested KNN semantic search, or what's technically an approximate KNN search, or ANN. And what that means is we're going to be using our vector embedding. So here's our embedding that we just created of our search criteria. And we're going to be looking for the 6 nearest neighbors. Now in this case, because we just want a list of the closest videos or the closest video segments that match that description, we are going to get 6 videos back. Now under the covers, it's looking for the 6 closest segments, but those segments are going to be divided across different videos. So let's just say we're looking for cars in a city and there's a particular commercial where there's a car driving through the city the whole time. We're not going to get that same video back 6 times in our list. We're only going to get it once. And since that car appears in there quite often, maybe it's at the top of the list, but we're going to get 6 different videos back. Now under the covers, it's looking at the score of each segment, but the list that we get back is a unique list of videos. Later on, we're going to talk about how do we get a list of segments back. So what are the highest rated segments that match our search? In this case, we just want the closest videos based on that search. So hopefully that made sense. Let's run that. and we can see that we got results back. Now we're not visualizing this. I'm just bringing back a list and I formatted that so you can remember from some of those Pydantic objects in our OpenSearch document structure. We have the video name, we have the title, which is what we generated. We have a score, and then we have the duration. So I want to know the name of the video, what the title was that was generated by Pegasus, and then what's the score and how long is the video. And you can change these fields. Those are just the fields that I extracted from what was returned. The only thing I didn't return is the embeddings. For this particular search, I don't need the embeddings. I'm not visualizing in it. I'm not graphing it. And the embeddings are very large. So unless you really need the embeddings, you want to exclude that. And you can see here that these are the videos, right? So there's a TurboTax video, Coca-Cola video, Amazon Prime TV show, Volkswagen commercial, Taco Bell Poppy commercial. So based on the search criteria of cars driving in a city, again, I only have 41 TV commercials in my index. These are the 6 videos using semantic search, and we can see the scores here. Again, we can also use filters. So we can do the exact same search, but we can combine that and look at other fields in our documents. We have the video name, the title, the summary, the keywords. We have duration. We have the type of the video, the length of the video. We can use any of those fields in combination with our semantic search to filter the search results. So again, I'm going to do the almost exact same search. I'm passing in the same embedding. I'm going to get a list of 6 videos back that most closely match my search criteria, but I want to filter that. So I'm going to look at the duration in seconds. That's the duration of the video, the overall video. And I want videos that are greater than or equal to 20 seconds and less than or equal to 60 seconds. So I only want commercials that are between 20 and 60 seconds. And that might be a common ask. I have a spot open. I have a 30-second spot open. Which commercials do I have that I can run? This is one way to do that. So this is a KNN semantic search with a filter. And we can go ahead and run that. And we can see here, if we just look at the duration, we see that we have a couple that are almost exactly the same, and that's standard 30-second commercial. You would expect that. But we have a 30-second, 30-second, another 30-second, a 44.8 second, another 30-second, 30-second. So we have 5 that are right on 30 seconds. If you round that off, those are roughly 30-second commercial spots. And then we have one that's roughly 45 seconds. None of our search results are under 20 seconds or over 60 seconds because we applied that filter. The next thing we want to do is what's referred to as nested KNN semantic search with inner hits. So I mentioned, right, we're getting a list of videos back, unique videos back. But underneath, what it's actually doing is looking at the score of each segment. So within a video, within a Pepsi commercial, within a Doritos commercial, we've divided that commercial into segments 2 to 10 seconds. And then each one of those segments has 3 embeddings. Again, visual text, visual image, and audio. When we do a semantic search, those embeddings are actually related to those segments. So what's really being returned is a list of segments with a particular embedding type. In the searches up here, we didn't show those. You just get a list back of 6 videos that match that, and that's accurate. But which segment within these videos was the closest match? Which segment in the Subaru Forester commercial scored 0.63971174, right? That score is actually related to the top scoring segment within this commercial. So let's take a look at that. Hopefully it'll make more sense when we look at the search results. So ran the same search. And again, the only difference is I'm displaying some more of the fields. Again, I've excluded the embedding. And I've told it which fields I want to return. So it's a nested search, and I said, return these fields. So I'm interested in the start time, the end time, and the embedding options. So again, I've run the query. I've called out some specific fields that I want, and I've excluded the embeddings. And again, returning a K value of 6. So our 6 nearest neighbors, or a list of 6 videos, which most closely match our search results. And we can see here, if we take a look at that, we can now not only see the first video that was in the top of the list in our previous searches was, again, the TurboTax commercial, if you remember that. And that scored a 0.685, roughly rounding off. So that was the highest score. That was the closest match, the nearest neighbor. But specifically, which segment within that 30 seconds was the segment that most closely matched our query? So if I had, imagine a 45 or 1 hour long or 2 hour long movie, and I had that same search, I want to know where in that movie. I don't want to have to play through 30 minutes, 60 minutes, or an hour, even in this case, 1 to 2 minute commercial in order to find that snippet. So we can use this search, and this actually tells me that segment 0, so on a 0-based scale, so the very first segment, scored the 0.685, which was the overall score up here. So these two scores are the same. And that happens to be the first segment. So again, segment 0 runs from 0 seconds to roughly 6 seconds. So if I were to grab the TurboTax commercial and I were to view the first 6 seconds, that is going to be the closest match to what I asked for. Now we can also see something interesting here. This segment, 0 to 6 seconds, or segment 0 for TurboTax, actually has 3 embeddings. It has visual text, visual image, and audio. In this case, the closest match came from the visual text embedding or segment. So that was the one that was returned first. If we look down here, visual search, here we can see this one starts at 23 and goes to 28. All these look like visual search, and there's ways to change that. We could change our search criteria filter only on audio. If we were looking for like a particular lyrics to a song, like that boom, boom, boom to the bass line. For the Pepsi commercial, I may say, hey, just look at the audio, filter only on the audio embeddings, which will make the search a little quicker. In this case, I didn't have any filters. Again, this returned the closest matches. And now I know where to go within that video to find the closest segment. What if we want to see all the segments and how they scored? Let's run that, and then I'll explain to you. So this search, you can see here, now I have the same 6 videos back. TurboTax is still number 1, followed by Coca-Cola. But now I can start showing multiple segments, and I can control how many segments I'm viewing here. So I probably have 3 on here. We'll take a look at the code in a minute. And we can see segment 0. Now that segment 0, so we had a score of 0.685 was the score. That was the highest score in our query, in our semantic search. And we can see here that segment 0 had that score, followed by segment 6, followed by segment 1. So 0, then 6, then 1. These are the top segments within this video that matched our criteria. If we go to Coca-Cola again, we can see 5 and then 18. So this is a little bit longer video, 62 seconds. It has more segments. Each one of those segments has multiple embeddings. In this case, you can see this was a visual text embedding, which scored the highest score. But the second highest scoring segment was actually a visual image embedding, and that was starting at 23 seconds. So this can be very useful. So not only which video potentially has the best match to my search criteria, again, this cars in the city, which segment or segments of that video can I find that car, that person, somebody scoring a goal, somebody climbing a mountain, whatever that key moment is, where can I find that dog, that cat, that car, that famous celebrity in the video, which segment or segments. That's why we want to use this type of search. We can continue on, so just kind of building in complexity. So now we have a nested semantic search. We're going to return all the nested hits, so all the segments. And we can also filter, so we can combine the semantic search with filtering and return all the segments and see the scores within that. Just returning certain fields, I'm not going to return the embedding. I want to return the start and end embedding option so we can display that. In this case, also interesting, I'm just going to filter on audio. So let me go back up, and for this case, I'm going to use the boom, boom, boom to the baseline. Let me just scroll up here. You remember when we created our embedding and we had cars driving in the city. I'm going to comment that out, and I'm going to create an embedding of this boom, boom, boom to the baseline. That's for a Pepsi commercial, so hopefully that will be the top result. And those are lyrics to a song, so I'm just going to search on the audio embeddings. And this, again, might take, unfortunately, 30 to 60 seconds. So we can see that was completed just about the same amount of time, pretty consistent, about 31.5 seconds. Really expect that to be, really a fraction of a second. If we're doing a high volume of searches, we want to get that embedding back very quickly. Let's scroll back down to our search. So this is our search, and you can see here I'm going to filter on audio. So I know those are lyrics to a song. I'm going to return 6, same thing. I'm going to, again, focus just on the embedding option of audio. So I'm going to return those, and I'm going to exclude the embedding because, again, I don't need the embeddings for this search. So let's go ahead and run that, and we're going to get the top 6 results back again. Haven't changed that. And if we can scroll up here, all the best moments are better with Pepsi commercial MP4 file. You can see that on YouTube if you watch that, and part of the lyrics are boom, boom, boom to the baseline. And specifically within this commercial, which is 30 seconds, so it's roughly a 30-second commercial, the 13th segment, the 12th segment, followed by the 11th segment is where that particular lyric or phrasing is repeated multiple times in this video, and that's where we find it. Now, if that's the only video where those lyrics are used, why am I getting multiple search results back? Again, this is K nearest neighbor. So what are the closest search results? What are the nearest search results? Although this one is probably the one I was looking for, there might be other ones that have songs. There might be other ones that have lyrics that have similar words or mean the same thing. So there's a lot of reasons why it might have returned additional movies. But I did ask for 6, and I did get 6 back. So again, in this case, the second one was LeBron James Prime Day Adventure commercial. That was a 60-second commercial. Again, you won't find those exact lyrics in this song. There might be music in that song. He might say words that are similar. There might be some similar phrasing. By visualizing it, we'll probably get a better idea of why that matched. That was K&N semantic search with nested fields, so returning all those segments and those scores, and then filtering on a particular nested field versus our original filter was on a unnested field, title or summary or keywords. In this case, we actually filtered on one of those multiple embedding fields. So within each one of those embeddings, we have the embedding option type, and we actually filtered on that. Within those nested embeddings, we filtered on a field within those embeddings. One last search, and then we're going to get into visualization. So the last search is radial search. This searches all the points within the vector space that reside within a specific maximum distance, or you can use minimum distance threshold from that text embedding, that textual-based query string, cars in a city, cars driving in a city. This uses squared Euclidean distance. In this case, I only have 40 videos. The search results are probably going to be identical. So again, you can remember we changed our query to the lyrics for the Pepsi song. And again, we see Pepsi came up first, followed by LeBron James. So that's the same. We won't go look at all these. They're probably the same. It's a very small index. There are reasons why you might want to use radial search, and you can also adjust the minimum or maximum distance. And again, each one of these fields also has reference back to the OpenSearch documentation. So if you want to learn a little more, just take a look there. That was our last search. Now what we want to do is visualize this. We get our searches back, we can list those, but oftentimes there's a visual component. Now there's no UI here. We haven't built a pretty UI in order to display these videos. We're just working out of a notebook. But you can imagine as you try to replicate a lot of the features of the TwelveLabs SaaS platform, which is a visual interface. They have a great UI. If you now are using Amazon Bedrock to call the models, create the embeddings, create the descriptions, using OpenSearch to store this instead of a TwelveLab index, you've now lost that visual component, that UI. And that's something you're going to have to recreate. So there's advantages of being on the Amazon platform, maybe versus being on the TwelveLab platform. Maybe your existing applications are already on AWS. But you will have to create a UI in order to visualize these search results. A couple different ways we can do that. Let me plot it, and then we'll take a look and see what it is. So this is doing the same search. This is search result 1. So if you can remember, when we did search result 1s, and we already ran that previously, that was with our cars in the city versus the Pepsi lyrics. This is just calling that. I haven't ran a new query. I just went ahead and got those query results that we ran earlier. And these are all numbered. So each one of the queries we ran, you can refer back to any one of those. You don't need to rerun it. Search results number 1 were just the straight up semantic search using that cars in the city. And those were 6 results. And then we're calling the keyframe. So if you can remember, I told you in each document, if we just take a look at one of those documents quick, and this is going to be a little extra work if you want to do it, but it also mirrors some of the TwelveLabs features. You remember in my last video, TwelveLabs does have a CloudFront endpoint where they have a keyframe. So if you want to visualize a particular video, or maybe you want to visualize the distance between your search and multiple videos, but instead of just having a name, maybe you want a keyframe that identifies that video. Or if you're doing search results and you want to have a grid of results and you want to have a keyframe to visually identify that video, you'll need that. So I created a CloudFront distribution, and then I have those keyframes in S3. They're protected. The CloudFront distribution accesses that particular directory in my S3 bucket, and I'm able to display those JPEGs that I created from FFmpeg. The keyframe is in the document, and then I'm just extracting that, and then I'm calling that URL and displaying that right here. And those are the images I get. So these are the keyframes that I generated for each video. You could also use FFmpeg more dynamically, and maybe you return this 3rd or 4th segment within a 30-second video. You could use that start time to generate a keyframe of that particular segment's start point. If it's 20 seconds in, create a keyframe that's 20 seconds into the video that reflects that segment, versus this is just happens to be maybe the keyframe within the second of the video, which doesn't do a bad job. But if you're looking at a particular segment, you might want to create multiple keyframes, one for each segment. And you could do that dynamically. The other way to visualize this is, and we're talking about nearest neighbor, right? So I have a search, I've created an embedding, I'm doing a semantic search, and it's returning those search results based on those vectors. Now, those are dense vectors, 1,024 dimensions. We really can't visualize that. In the last video, I demonstrated visualizing those in 2 dimensions and 3 dimensions using PCA, or principal component analysis. Principal component analysis is good, but for high dimensionality vector embeddings, it doesn't work as well. And I'll show you a comparison. I'm going to do it with both. So I'm switching to T-distributed stochastic neighbor embedding, or TSNE, versus PCA. And we get much better separation, especially for visualizing high dimensional vector embeddings and wanting to visualize that in 2 or 3 dimensions. TSNE works much better than PCA, which I demonstrated in my last video. Again, there's reasons to use both, and I'm going to use them both here to show you the difference. But in this case, let's do the same thing. So I'm going to do a basic search. The reason I have a new search here is, in order to visualize my embeddings, I need to reduce the dimensionality of those down to 2 or 3 dimensions. We'll talk about that in a minute. Well, in order to do that, I need those embeddings. So if you can remember, in my other searches, I did not return the embeddings because obviously they're large and I want to get a quick search results. I just want particular fields that I need to use for my end user to display to my end user. In this case, because we're going to reduce the dimensionality of those embeddings and then display those in 2 and 3 dimensions, I need the embeddings back. So I'm not excluding the embeddings. So that's why I have a new search here. So let's run that. Very simple search. So our K value is 9 nearest neighbors. I would expect 9 search results back. The next thing I want to do is create a new object. I return several fields. For my results, for displaying the results, all I need is the embedding and the video name. I'm going to reduce the dimensionality of the embedding, and I'm going to use the video name as part of the output in the legend of the model. So again, this is just taking my search results back, and then I'm filtering those down a little farther just to the fields I need. Again, we used PCA last time. This time I'm using TSNE. And you can see here really the main thing, taking that 1024 dimensions and reducing it down to 2. We're going to do the same thing later on with 3 dimensions to display the data in 3 dimensions versus 2 dimensions. We'll start with 2. So let's run that. And we should see, here is an example. So all the best moments are better with Pepsi. That's the number 1 result. I got the 9 closest search results back. Reduce those 1024 dimensions down to 2 dimensions. And we can just see that here. So instead of a 1024 dimension vector embedding representing this video or that segment within a video, we only have an array of 2 floats which represent that versus 1024. So just displaying that so you kind of understand behind the scenes what's going on. To really understand that, let's visualize it. And this will make much more sense. So I'm using Plotly. I used Plotly in the last video. I like Plotly. There's many other libraries you could use. But key here, now we can start to visualize it. So instead of saying, here's the 9 closest videos that matches your particular search, which was those Pepsi lyrics, we can actually see the position within that latent space or that vector space, which has been reduced down to 2 dimensions. We can see the relative proximity, and we can see here all the best moments are better with Pepsi. I just truncated it for space here, but we can see that, relatively the purple dot here is the closest one. That also happens to be the top scoring search result. And if you can remember, LeBron James was the second closest one, and he's down here. Now, what's interesting is, although he had the second highest score, in terms of the distance, when we reduce the dimensionality down and plot those, that doesn't always correspond. But again, so it depends on what you're looking for, how you want to visualize this. And there's certainly search engines that visualize it. And you can click here and say, oh, I want this video. You click on that in TwelveLabs platform. If I were to click on that, the video segment would actually come up over on the right-hand side of the screen, and I'd be able to view not only the video, but that segment. So I can use this type of search, or I could just use a list and click on the items in the list, or I can have a list with a little keyframe preview, or I can do it this way where I have more of a visual representation in terms of the proximity of the search to their nearest segments, and then I can click on those and maybe view the video or download the video or view the segment. So this is 2 dimensions. You can imagine we can do the same with 3. So again, our end components is 3 versus 2, and we're doing the same thing. So we're going to reduce those 1024 dimensions down to 3 dimensions. Again, all the best moments are better with Pepsi. That is the commercial that contains those lyrics we're looking for. And instead of 1024 dimensions, we have 3 floats in our array. In the previous example, we used the X and Y dimensions of the chart to plot those 2 floats. In this case, 3 dimensions, X, Y, and Z, we're able to plot each one of those values in a 3-dimensional space. This may or may not be a better way to visualize the proximity of our search results, which is right here, to the nearest neighbor. So again, all the best moments. So if you remember our 2-dimensional display, let me just call that back up again here so we can see this was the 2-dimensional display, not very interactive. Same exact data, almost identical here. Code's just a little different. Still using Plotly, using a 3D scatter instead of a scatter. Can move this around. We can also make it just a little smaller. I can rotate that in space. So we can kind of take a look and see, here's our search results, and then we can kind of see the proximity of the search results in 3D space. I also had a little animation with Plotly. You are able to automate this. Sometimes it's hard to get this exactly. And then you start turning it and it goes all different which ways. Reset it and we hit play. It'll just rotate in space, which just makes it a little easier to visualize. And then you can imagine as an end user, you click on the one you want and it takes you into that video. So instead of just looking at a list of scores that are in ascending order, I actually get a visual search results that I can then click through or click on. So that's how to visualize that data. What if I just want the 6 closest segments? So forget giving me a unique list of videos. Give me the highest scoring segments. Focus on the segments, not the video, because I want to actually plot all of the segments to show you the relationship between the segments. My K value is 50, my size is 50, so 50 videos, I only have 41. And then I'm going to return all of the embeddings, and actually I think 100 is a max. So let me just make sure I get all the segments, set up a way here to list those. And I'm going to list all of the segments. Instead of one segment or the top 3 segments, we can display all of the segments. Technically, I should have all 41 videos. I should have 3 embeddings for each segment. I should have all of those segments, all of those embeddings returned in a much larger data set. And then I can really focus on the segments and how the segments score, how close they are. So let's just look at the top segment results. So again, I can overall in that entire list, extract just the segments. So give me the file name, the start and the end based on the score. So sort by score and just give me a list of of segments. Forget about the videos. I don't want 6 or 9 unique videos. I want 6 or 9. In this case, I return them all, sort them in order, and then give me the top results by segment. Give me a list of segments across all the videos, not a unique list of videos. And we can see here that for the query that we had, which again, since I reran this, the last embedding that we created was the boom, boom, boom to the baseline, the lyrics. We get the Pepsi commercial back, and we see that segment 15 to 23 is the best match. And again, so now we're focusing on segments versus overall videos. Give me a list of matching segments regardless of the video versus a list of unique videos. And we can display all those. So let me run this. I used PCA. Now you can remember we switched to TSNE versus PCA, or principal component analysis. Two things to notice here. One is, and I'll show you the difference in a minute with TSNE, not a lot of separation here. So these represent all the segments, and I'll talk about why there's 3 clusters here in a minute. But these represent all the segments. The problem is you don't see a lot of groupings. There is a commercial on Pepsi. There's a Doritos commercial. There's a Volkswagen commercial. These seem very random, though, the placement. The one thing it does do, though, audio, visual text, and visual image. Although these were all created with the same model in the same latent space or vector space, the audio commercials are tightly clustered. The image, visual image, and the visual text are all tightly clustered. What does that mean? May affect the way you do search. So the relative distance between these in 2 dimensions is different. If you were visualizing these, if you have lyrics, maybe you just want to focus and only return the audio embeddings versus the visual. So let's do the same thing though, and we're going to display it using the T-distributed stochastic neighbor embedding. And this is again better for high dimensionality vector embeddings to visualize those. So same exact set. I also added k-means clustering to this. I'm able to look for clusters within the data. And I've just created, again, with Plotly, translated that into these dotted lines. But you can see here, very different, right? Instead of 3 clusters, we appear to just have 2 clusters. Again, audio, you start seeing some clusters here. We see like this is the anti-smoking commercial. This is the Heinz commercial, Harrison Ford, and the Jeep commercial that was in the Super Bowl last year. Some commercials don't have a lot of audio. Some commercials have spoken word. Some have music. Some have music with lyrics. That could explain some of this. What is really interesting though over here, when you look at the visual text and visual image embeddings, you start seeing tight clusters. You can see here that we have the visual embeddings and then closely associated are the images. This is a Reacher commercial. And what makes this interesting is now we can start looking at the videos and the relationship not between the user query. So I didn't plot the user query. I only plotted the videos here. The relationship or the distance or the similarity between, in this case, commercials. So I have a commercial. Which commercials are similar to that commercial? But in this case, we're using K-nearest neighbor. And then we're using TSNE to reduce the dimensionality of those embeddings, and we're plotting those and visualizing those. Let's just take this, and I'm going to zoom in. So these are relatively close. And if we look at each color represents a commercial. So even if the embeddings, these are visual and these are image for this first Indian commercial to win a national award, they're the same color. But here we see 2 different colors, but the 2 clusters are very close to each other. This happens to be an Indian commercial for Most Loved Food. So this is a food commercial that's an Indian commercial, so not English. And this is another Indian commercial. These are both Indian commercials. Now these are not the audio. These are both visual image. So visually, I'm going to assume that if we watch these 2 commercials, there's a lot of similarities between them. Let's take a look at one more. Here we see both in red. So this represents the same commercial. These are probably 2 different types of embedding. So these are visual image, and then these are visual text. Same commercial, 2 different types of embeddings, but again, very closely related, which is what you would expect. Same thing here. This is the Volkswagen commercial, the image and the text clusters. And maybe one more. So let's look at this area here. So there's a lot going on here, but we can see here similarity. So here is the Temu big game. So this is a Temu commercial from 2024. And if we look over here, Super Bowl commercial. So I'm wondering if this was a Super Bowl commercial. So there's some similarity here. These are visual image embeddings. These are also visual image. So visually, there does seem to be some similarity between the Doritos Super Bowl commercial with Jenna Ortega and the Temu big game ad. I'm assuming that's a Super Bowl ad, and maybe that's the similarity. We can also see here's the Skechers commercial with Andy Reid 2025, and that's also very close to the Little Caesars best thing. So I don't know what Skechers shoes have in common visually with Little Caesars, but using this technique, they do seem closely related. So a lot of information you could derive from here. Again, the audio, although there are some groupings, audio being very different, we see quite different things here, and it's not as clear cut. And that could just be the nature of the audio in the commercials. Really interesting. Instead of just looking at a user search, we can start looking at all the assets and how they relate to each other in space. And TwelveLabs does this really good on their platform, much better than this simple graph. They have some really nice visualizations that allow you to visualize all the segments, see these clusters, and then kind of click on these and drill into each particular segment to get more information. So just trying to represent that here in a notebook using Plotly and reducing the dimensionality of our dense vector embeddings. So that's it for our demonstration. So we demonstrated using the TwelveLabs Marengo and Pegasus models on Amazon Bedrock, and we used OpenSearch. And again, you could use OpenSearch locally, or ideally use Amazon OpenSearch serverless and get the same results, how to create documents from the results of those models, which we generated the embeddings and the summaries and the titles and the keywords from, combine those into OpenSearch documents, index those, and then be able to perform a number of advanced searches and visualize those search results using OpenSearch and some popular plotting libraries. Thank you very much. I appreciate your time today.